Hi, everybody. I hope you're doing well. This is Mr. Gallagher here, and welcome to section 23C here in IB Math. Again, I hope everyone's doing well and you're adjusting to distance learning and hopefully taking care of everything that you need to be taken care of. So, today we're going to be talking, continuing with chapter 23 about discrete random variables. We're going to talk about expectation today. And so again, these notes will be on eCampus under the notes section as always, and then we have an assignment here at the end for you to submit. And as always, if you have any questions, please let me know in the discussion boards. If there's a lot of questions about certain assignments, I'll even probably maybe post a video or work some problems out for you. So ironically, this is just like school for me because as soon as I started recording, someone started mowing their lawn, and I feel like this is just like they're mowing lawn outside my classroom. So if you hear a slight buzz, that's what that's all about. Anyway, so it's just like school. All right, so let's talk about expectations. So we've been doing probability, right? So let's say I roll a dice, right? What's the probability of rolling a 6? Well, we know that's 1 out of 6, right? But let's say I roll dice 120 times. How many times am I going to get a 6? Well, there's no guarantee, right? But we do have an expectation because there's a 1/6 probability of it being a 6. Then we know that the expectation of of getting a 6, we roll 120 times, is we're going to expect about 20 of those 100 rolls to be a 6, right? Now that's not guaranteed. That's just based on the probability, right? And if we roll 120 times, maybe 18 of them will be a 6. Maybe 30 of them will be a 6. Maybe none of them will be a 6. But our expectation is that 20 of them will be. And if I rolled the dice 120 times every day for a year, then you would really think that the average of my daily sixes, even if I didn't get 20 every day, you would eventually figure, well, the average of how many sixes I got every day would be 20, right? If I rolled the dice 120 times every day for a year, if you look at what is the average number of sixes I got every day, you would figure it'd be really close to 20, right? Assuming it's a regular dice and everything else too. So that's what we're talking about today. We're going to be talking about expected outcomes. And what I just did was a formula there. So we're going to be looking at the mean or the average result, and it's going to be the sum of all of those different occurrences times the random variable x, and that's what that formula means here. And it's a lot easier to see when we look at examples. So let me give you one here. If it says each time a footballer kicks a goal, he has a 3/4 chance of being successful. For a particular game, he kicks 12s. How many? 12. He has 12 kicks. How many goals would you expect him to kick? Well, as we said up here, we're looking for the total number of events times the probability of that event. So we're going to be multiplying. So in this case, the total number of events is going to be 12, right? So we have 12 kicks, and we're going to multiply by the probability of 3/4, and we're going to get 9, right? Because the probability of him getting a goal is going to be 3/4. Now, we could do this. It's not guaranteed he's going to get 9, right? But we could. What if he kicks 12 goals a day over multiple days? We'd think the average would be really close to 9, and that's what we're talking about here when we talk about mean. So let me give you another example. And hopefully that makes sense, right? 12 times 3/4 is 9, and 12 kicks and 3/4 probability, I expect to get 9 goals. Here's another one. We did this problem earlier. This was that how many magazines do you expect someone to get? Right, when someone walks into the store, and we found out the probability that a person will buy X number of magazines, right? So the probability of them buying 1 is 0.23. The probability of them buying 5 is 0.05. We made a spike graph for it and everything, right? So we talked about the number of magazines purchased by a person. Well, what if we wanted to look at the average number of magazines purchased overall? Well, that's going to be based on the probability, right? And it's going to be based on the probability for each of those numbers occurring, and then we would expect that would be what we expect the average to be for the day. Now, that doesn't mean it's guaranteed, but then over a long period of time, we could get the expectation of number of magazines to be purchased. So what I do here is, again, we look at the sum of all of the different random, look at the sum of all the probabilities times the possible random variable values, right? Because the random variable x is 1, 2, 3, 4, or 5, and we're going to multiply each one of those times their probabilities. And if I do 1 times 0.23 plus 2 times 0.38 plus 3 times 0.21 plus 4 times 0.13 plus 5 times 0.05, I multiply those out, add them together, then I'm going to get 2.39. So on average, if I looked at these probabilities every single day, the average number of magazines purchased per customer in the long run is going to be 2.39 magazines. Obviously, you can't purchase 0.39 of a magazine, but that's going to be the average magazines purchased per customer. And that's what our expectation is going to be. Here's a great application of that idea. Of this idea of expectations. We're going to call it fair games. And in gambling, you always look at what your expectation is when playing a game. The idea is if you have to pay a certain amount to play a game in gambling, you're going to get a payout. And obviously, you as a player, you want the payout to be more than what you paid on average. Most games don't work like that. If they did, casinos would go out of business. But if you expect a game to be fair, a fair game, so just real quick, let me back up here. Expected gain, right, is the expected return or payout from the game, less the amount that it costs them to play, right? So it's what the payout is minus what it costs, right, to buy in. Ideally, you want that to be a positive number. You want to be able to get more than it costs you to play. But again, casinos don't work that way because they would be out of business. However, we would say a game is fair if the gain is going to be 0, and that's what a fair game is. So again, a game of fair is if our expectation is going to be 0. So let's look at an example here. We have this game of chance, right? So let's say it's a spinner, and they're labeled 1, 2, 3, and 4. And the player wins the amount of money that shows up on the spinner for each number. So what we want to determine is what would be the expected return for one spin of the spinner. And if it costs you $5 to play the game, what's your expected gain going to be, and then would you recommend playing this game? So let's say I had a spinner, and I had 1, 2, 3, and 4, and if you spun 1, you got $1, and spun 2, you got $2, a 3, you got $5, and you spun a 4, you got $8. Well, if it didn't cost you anything to play the game, of course you're going to play because you're always going to win money. But what if I said, well, it's going to cost you $5 to play this game? You're going to say, well, if I spin a 1 or a 2, I'm going to lose money. If I spin a 3, I'll break even. But if I spin a 4, I'm going to make $3, right? Well, it looks like I lose some money here and make some here. Is it fair? Should I play this game? So let's figure out the probability. So first of all, what am I going to do? How am I going to get my expected outcome? So we're going to call that expected outcome of, let's get a thicker marker here. My expected outcome, we'll call that E of, we called it E of X up here. Let's call it E of Y down here for this one. And what are we going to do? We're going to multiply each of the outcomes, right, by the probability. What's the probability? Assume it's a fair wheel. Each probability of each number is going to be 1/4, right? So I'm going to say 1/4 times $1, right, plus 1/4 times $2, plus 1/4 times $5, plus 1/4 times $8. Let's see what I got here. Well, that's going to be, what, 1/4, and that's going to be plus 2/4, and that's going to be plus 5/4, and that's going to be plus 8/4, and I add up all those together, that's going to be, what, 16/4, which is going to be 4. So my expected outcome is going to be $4. Now, obviously, $4 isn't on the wheel, right? But I can expect if I spin this over time, over the long run, my average winnings for every spin will be about $4. So that's what my expected gains are going to be. Or that's what my expected return is going to be, sorry. What's my expected gain? Well, if it costs $5 and I only win $4, well, $4 minus $5 is going to be -1. I'm going to lose $1 in the long run every time I play. Might I get lucky sometimes? Sure. But on average, I'm going to lose $1 for every time that I play this game. So would you recommend? I would not recommend playing this game. Unless I'm the one hosting the game, and if you want to play and pay me $5 to spin the wheel, I would recommend that you play it a lot. That's basically what it explains down here. So here's what I'd like you to do for section 23C. There's 5 problems. Some of them have multiple parts, but they're all basically along these lines. So check these out. There will be an assignment in eCampus that you can take a picture and submit. Seems like that's going pretty well so far. And we'll check this out for section 23. And again, if you have any questions, please let me know on the discussion boards. All right, take care. Talk to you soon.